Okay, 7th of April 2025. Chapter 4 is about thread and concurrency. Difference between thread and process would be process is one process. A thread only has its own register, shares PC, and shares code, data, and files. Because when white thread came up, we can think of update, display, or fetch data, or spell checking, and sorts of network requests. We need a lot of things we should do. So thread came out, and we can do multi-threading. When we do so, when we think of multi-thread for server architecture, if client requests, then we should create new thread to service the request, and after that, server will resume listening for additional client requests. The benefits will be the continued execution, which is responsiveness, and we can do resource sharing easier than shared memory or message passing, and cheaper than process creation. Also, process can take advantage of multi-core other architectures. Multi-core processing, there can be parallelism and concurrency. For parallelism, there is data parallelism and task parallelism, which is data parallelism is on same data across multiple cores, same operations on each. For task parallelism, we distribute threads across cores, each thread performing unique operation. There's Amdar's law, which says about performance games from adding additional cores. S is serial operations, and N is addition processing cores. So we can check if we can notice that as N approaches infinity, speed up approaches 1 over S. And we can split thread as user thread and kernel thread. There will be many-to-one cases and many-to-many cases. Kernel thread knows which user thread should be assigned with kernel thread, and user thread is controlled by bit thread. Kernel is scheduled by operating system. In two-level model, except that it allows a user thread to be bound to kernel thread. It will be seen. There's some thread libraries. pthread, which is working user level. And for Java, there's implementing runnable interface, and we can make creating a thread by a new thread or waiting on a thread by that join method. And there's also implicit threading, which is thread pools, fork join, and open MP. Such method exists. For thread pool, it is creating a number of threads in a pool where they await work. It will be the advantage is it will be slightly faster to service us because with an existing thread, then create a new thread allows the number of threads in the application to be bound to the size of pool, and separating tasks to be performed from mechanics of creating tasks or rules different to this for running tasks. Fork and then fork join. The threads are not constructed directly during the fork stage. And there's some method. So fork join is abstract base class. So there's our recursive task and recursive action class. If then fork join task, recursive task returns a result, and recursive action does not return a result. For OpenMP, we can use it by star pragma OMP parallel, which we can identify parallel regions block of code that can run in parallel. And there's fork and join for fork. In Unix system, there are two different fork, which is duplicate only the calling thread, or there's another option for all threads. The exact is replace the running process, including the thread. And for signal handling, signal handler is used to process a signal. Signal is delivered to a process. Signal is handled by one of those signal handlers. And every signal has different handlers. And for thread cancellation, thread to be cancelled is target thread. And there are two approaches, which is asynchronous cancellation, which immediately finish target thread, or default cancellation, which allows to periodically check. So there is three mode, which is off, default, and asynchronous. And there's a concept of thread local storage, which is allows each thread to have own copy of data, useful when you don't have control over the thread creation process. It's different from local variable. It's more similar to static, but TLS has its unique to each thread. And for more specific example, there will be window thread and there will be Mac Linux thread. For window thread, window API implements one-to-one mapping in kernel level. One-to-one mapping in kernel level. Register set representing state of processor. Separate user and kernel stacks for when threads run in user kernel mode. Private data storage are area used by runtime library and dynamic link libraries. Register stacks and private storage area are known as context of thread. And there is three primary data structure is included, which is executive thread block, includes pointer to processor to which thread belongs to K thread. And kernel thread block, which is scheduling and synchronization info, kernel mode stack, pointer to TAB, and kernel space. And also there's thread environment block, which is thread about thread ID, user mode stack, thread local storage, and user space. And for Linux thread, creation is done by clone core, allows a child task to share the address space of the parent task. And we use a flag control behavior, which is clone fs, clone vm, clone weekend, and clone files, which is file information system, system information is shared. The same memory space is shared. Signal handlers are shared, and the set of open files is shared. And struct task struct points to process data structure. And for chapter 5, it is CPU scheduling. CPU scheduling, the basic concept is there's CPU burst and there is IO burst. In CPU burst, we load, store, and add, store, and read from file. In IO burst, we wait for IO. So when process switches from running to waiting, running to ready, and waiting to ready and terminate, it is non-preemptive, and except that or is preemptive. If for condition is non-preemptive. And for dispatcher, which is gives control of CPU to process selected by short-term scheduler, switching context and switching to user mode, jumping to proper location in the user program to restart the program. And the core things are, these things are our core scheduling criteria: CPU utilization, throughput, and turnaround time, and minimizing waiting time and response time. So there is first come, first served scheduling, which is in a sequence of how it comes, we process it. And there is shortest job first, which is the shortest time remaining goes first. For shortest time FJF, we also use this chart to predict what should come next. We can predict the length of next CPU burst. We would call it exponential averaging. And there is shortest remaining time first, shortest job first. Shortest job first. The shortest remaining time first is preemptive version of shortest job first. And there is round robin. Each process gets a small unit of CPU time. We call it time quantum. And then timer interrupts every quantum to schedule next process. So we calculate basically average waiting time. And for priority scheduling, the problem is starvation. Which is low priority process may never execute. The solution is increase the priority of the process. We also use it with round robin together. And there's multi-level query, which is one of the solutions. And for thread scheduling, we use PCS, which is process contention scope, and SCS, system contention scope. In PCS situation, a thread computes separate in its process, but in SCS situations, thread computes all together. Pthread scope and Pthread scope system use PCS, and system use SCS system. Mac and Linux both follows Pthread scope system, which is SCS scheduling. Multiprocessor scheduling in this situation. There's multi-core CPUs, multi-thread cores, and NUMA and heterogeneous programming. In symmetric multiprocessing situation, every processor is self-scheduling. Each processor may have its own private child thread. Multi-core processor. This core has more than 100 thread, multi-threaded multi-core system. Where in this situation, two level of scheduling work. First is we have decided which software thread to run on logical CPU. And second is how this core decide which hardware thread to run on physical core. I actually don't know the clear difference each other. And for real-time operating system, tests should be running deadline. Soft one is they have priority, and hard one is all the tests must have deadlines. And there's event latency for interrupt latency and dispatch latency. Interrupt latency is time from arrival of interrupt to start of routine that service interrupt. And dispatch latency is time from schedule to take current process off CPU and switch to another. And for multiprocessor scheduling, if it is symmetric multiprocessing, there is load balancing, push migration, and pull migration. And there is concept of processor affinity.